Hey everybody, Mr. Stewart here, and welcome to this second video on the binomial distribution. So last day you ended up watching a video and I posted a few questions on the board in terms of reflection. So the first one asked you about the characteristics of this particular type of distribution. Now, if you said that they consist of independent trials where there are two outcomes, generally named success and failure, then you've got an understanding of what a probability distribution, rather what a binomial probability distribution is. Also, you're asked about the significance of the formula that represents the probabilities associated with this type of distribution. So, the n represents the number of trials, r is the number of successes, P is the probability of success, whereas Q is the probability of failure. So if the probability of success is P, then Q is determined by calculating 1 minus P. So the remainder of the screencast is going to focus on the application of the binomial probability distribution. We're also going to look at some graphing as well as calculating an expected value. So here is our main example. So the probability of recovering after a particular type of operation is 0.5. So a 50% chance of recovery. If 8 patients undergo this operation, I would like for us to do a few things. So one is to write the function defining the distribution. So that means we need to go back and take the equation provided and use that to begin representing a solution to this problem. So our first step is to take the base relationship and then, based on the information provided in our problem, we'll then go ahead and doing some fancy highlighting here. Let's see if I can't line all of this up. And there we go. Now, not exactly as lined up as I would like it to have been, so let's move things just a little bit more here. And there we go. So if you do follow the color coding that's throughout, you can see how each value in the main problem is being mapped into our given formula. Okay. Our third step then is going to look at any form of simplification that we can do. This will not happen in all problems associated with the binomial distribution, but it will in this particular case. So notice how this particular power, 0.5 to the r, has the same base, that is 0.5, as this power, 0.5 to the n minus r. So under this particular circumstance, okay, so let me highlight these here. Okay, so special notice here, because the bases of these powers are equal, okay, the multiplication rule for exponents, right? If you remember those rules from the past, the rule for multiplying powers that have the same base told us to add those exponents. So if we then add the exponents, so r plus n minus r, notice that r minus r equates to 0, as those are what we say additive inverses, so they subtract out to 0, and we're left with 8 choose r multiplied by 0.5 to the n. So that particular formula will allow us to calculate the probability of every particular success. So if the discrete random variable x, which represents the number of successes, could take on the values of 0, 1, and all the way through to 8. And that's what we'll do next, is we'll start using the relationship to represent. Okay? So it says here in part B to determine the probability distribution for the number of recovering patients. So when we see or hear the words probability distribution, what we're being asked is to visualize all the possibilities. So every particular probability based on each and every particular number of success possible, we want to visualize that. So we have a couple of ways of doing that. So we can represent it in terms of a chart or table format. We can also graph them out. So as far as R is concerned, what we'll do is we'll just map out the number of successes. So I've filled in 0 and 1 and left the middle blank because you'll see that through patterning, the representations are all the same. The probability of x equals r, that is nothing more than taking the relationship and then substituting values. So the value of n and then changing the value of r as we go through. Notice that the value of the exponent in the power of 0.5 to the n happens to be 8 all the way through. And recall that was due to the fact that the base of the power in our relationship here, go up a little bit further, happened to be 0.5. Okay, so if they were different, like 0.6 and 0.4, bases being not identical, we would not be basically collapsing that power down into one base. Okay, so you'll see that in subsequent examples and work through the text that has us focus on that. One thing that we can do is we can evaluate these expressions. So the approximate values you'll see underneath this screen shade. For most of the work that we will do, it's probably best that we leave the calculations until the very end or apply technology to calculating those values, just so that we don't introduce a lot of error. So here are those values. So for 0 patients recovering out of the 8, okay, there's about a 0.004. That's not as a percentage, that's just a decimal value. So it's a very small percentage of patients that would not recover. 0.03 or 3 out of 100 patients, that is in the case of 1 success, okay, that relates to 3 out of 100. So leaving the middle blank, of course, and then you can see that these particular probabilities are identical to these as there's symmetry with this binomial distribution. And you can see that certainly with the combinations. So 8 choose 0 has the same value as 8 choose 8. 8 choose 1, which equals 8, also has the same value as 8 choose 7. And because these powers happen to be all 0.5 to the 8, I think we can see and appreciate how these values will be the same. This symmetry that we see with this particular distribution, and again, this is not the same for all, and we can model that using some technology. You're going to see that coming up in the graphs. Okay, next. So this video will be a little bit lengthy. In fact, what we can do is we can likely pare it down or cut it back down into 2 videos. So we should do one that focuses on some of the representation and completion of the example, and then we'll do a second one which really focuses more on what these distributions can look like. So I'm going to show you quickly here using an online graphing calculator. If you go to the Wolfram Alpha website, and I've also put the link to the site in OneNote. Okay, so if I were to bring up OneNote right now during the course of our filming or recording, just take a moment for that to load, and I'll just give you a visual on where that link is so you have quick access to it. In fact, when you're watching the second video, or even this one, you might even consider pausing and then going into the website for the graphing and sort of experimenting with that and then returning back to the video. So you can see here under topic 13, important links, you've got video number 1 from last week, and down here is link to the graphing calc. I will be posting the video links here to 2 sources. Edpuzzle you can use over Wi-Fi in the school, whereas YouTube is a little difficult to use on Wi-Fi. For YouTube in school, you'd have to use your data. So you've got a couple of options there. Getting back to, let's just check our time on our video. We're up to about 10 minutes. So what we'll do is let's take a look at graphing this particular binomial distribution. So I'm going to head into the Wolfram Alpha website, okay, and it's called the Binomial Distribution Calculator. And by default, it sets up a graph here, not related to our question, but something that we can certainly take a look at. Looking at the p-value here, it's a 60% success rate, meaning the Q value, or the failure rate, would be 40%. The number of trials here is 10, okay? And then we're looking for the probability that we have 4, that is more than 4, successes. So remember, X is that discrete random variable is the number of successes, and here we're looking for those more than 4. If I were to submit this information to the calculator, what it's going to do is it's going to produce a particular graph, okay, along with some probabilities. Okay, so it's actually calculating the probability of all successes of greater than 4. So it's really summing up or adding together the number of probabilities for x equals 5, 6, and all the way up to 10. That's the probability here. The graph below looks more like a dot plot. Okay, so it's plotting the specific relative frequencies or probabilities. Okay, so for 4 successes, the probability is here. Roughly about 0.15 or 0.115, I guess, roughly. So you can sort of see with the success rate of 0.6 and 10 trials, you've got this beautiful looking distribution, which does have some symmetry. It's not completely symmetrical. You can see that the first few entries for 0 and 1 successes aren't really being registered so much, but you can see that there isn't that much symmetry based on where those values are. The values that are highlighted in red are the cases or the successes that we're really interested in, as indicated here by the 4, the 0, 1, 2, and 3, including the 4, are kind of in a lighter shade of blue, as they're not the cases that we're after. Okay, so a great way to visualize the distribution and to calculate, by the way, probabilities. Okay. So what we'll do, let's go back to our problem, and what we're looking at, recall, let's go back to the main problem, is a success rate of 0.5 with a value of n equals 8. So going into the Wolfram Alpha calculator, let's reset those values. So n is 8 patients, the success rate is 50%, and what we're looking for in this case is the probability. In fact, as it gets a probability, we are looking for just the distribution. Determine the distribution of recovering patients. So what we'll do is we want to include all patients, or all cases. So if we're going to include all cases, we have to indicate that by a particular range. So what we'll do is we'll say 0, which is the least number of successes, is less than or equal to x, which is less than or equal to 8. So it means that the number of successes is between 0 and 8, but with the equal signs, it also includes them. So let's submit that information. And here you have a binomial distribution. Just scroll down here a little bit, and there it is. Okay, so a beautifully symmetric graph. Okay, so you can really see the symmetry between 0 and 8 successes, between 1 and 7, 2, and 6, and so on and so forth, with the greatest probability of success occurring for 4 patients undergoing that operation at any given time. Okay. So that's a quick demo on how to use the Wolfram Alpha calculator. Your completed lesson notes, I would highly recommend that you use Sketch and or maybe do some screenshots in using the graphing calculator and then add them into your own notes, be it printouts or be it something that you store as a digital note in your own OneNote binder would be a great idea. So here, I'll just keep this so for posterity or for looking back on. What I'll do is when I produce the note, you'll have the screenshot that's there. Okay. So in the next lesson, we'll come back, we'll take a look at more reasoning graphically with this distribution and with a few others. But I would like to wrap this one up with some expected value. Just want to check our time here. We're up to 16 minutes. So let's finish off with expected value. So many of these particular questions sort of follow a similar procedure, okay? So hopefully your understanding is being developed around the topic, not just through the examples, but through some of the graphing and some of the things that have been said throughout, as well as your own experiences up to this point in time. But generally speaking, we look at setting up a formula. We try to develop the many cases that would comprise the distribution, through a chart or through a graph. And then typically we're really interested much of the time in expectation, which is the predicted average from any particular experiment. And in this case, an experiment involving binomial events. That's, experimentation where there's 2 outcomes. So what we can do is we can utilize the formula provided at the beginning of the unit. So using the actual probability distribution. So just to define this again, the E of x represents the expected value for the random variable x. And this symbol here, this Greek letter, okay, represents the sum or to sum. It's a summation symbol. So the lower value, actually this limit here, the lower limit of what we call an index, in this case is going to tell us the first case, right? So the first case for us was 0 successes, and will be the upper limit in our case, which would have been the 8th term, or the experiencing 8 successes. So what we'll do is we'll go ahead and we'll utilize that expression and expand it out to take into account 0, 1, 2, 3, all the way up to 7 and 8 successes for this experiment. Method 2 is a very shorthand method, and it's basically what we would end up using moving forward is there by algebraic proof. There's a complicated proof that one can find online that takes us from this definition here and into that one. That could be something you might see in some upper level senior math at university level. Okay. So step 1, what we'll do is we will identify the lower limit of the index and the upper limit of the index, so 0 and 8. So the numbers 0, 1, 2, all the way through to 7 and 8 would then end up occupying the place where you see I. Okay, so the letter I indicates the index value. So step 2, we'll go ahead and we'll substitute the index values in, and then we'll represent as we were previously when we were dealing with the introduction to the unit involving expected value. Okay, so you can see the number of successes being multiplied by the probability that that success would occur. Okay. So upon calculation, if we were to determine all of the decimal values, okay, so if we did this by hand or using some technology, you can see I'm approximating here using that symbol. So I am rounding some values as I'm going through, but if you were to calculate it with a large or a greater degree of precision and you're using technology, you would produce an expected value of 4. And I think that should make sense with a 50% success rate and 8 people undergoing the operation. So at any time there are 8 people undergoing this operation, we should expect 4 patients to recover. Okay. So what that means is the predicted average, or over the long term, if we did many samples of 8 people, so 8 people on Monday, Tuesday, Wednesday, Thursday, and every day from here on out, we would expect to see 4 people recovering. Okay, so just using our common sense. Or what we can do is we can use the expected value relationship n times p, and we can calculate half of 8 being 4. Okay, so that's the end of the first video. We'll come back to the second video, which is really going to focus on a graphical interpretation of binomial distributions, and also graphical techniques that you can use for a number of probability distributions moving forward.